we start discussing with him neutrino astronomy, ice fishing for neutrinos. Thank you.
Yeah, thank you very much, Manolis. Thank you very much also for inviting me to talk about neutrino astronomy. In the next 20 minutes, I will try to present 80 years of research effort and discoveries in the field of neutrinos. I have added to the original title, Neutrino Astronomy, the ice fishing for neutrinos, because this is really related with the current work that is taking place in the field. And I will try to give you an overview in this framework. So our aim, working with this great team that I have the pleasure to share common visions, is to really try to introduce frontier physics issues to school classrooms. So really the starting point and the trigger for all these activities are the current Nobel Prizes in physics. So back in 2015, the two representatives of two major collaborations, Super Kamiokande in Japan and Snow Lab in US, they are getting the Nobel Prize for the discovery of neutrino oscillations, which shows that neutrinos have mass. So for us, the main aim is how we can really transfer this information to first teachers, because we really believe that the teachers have to be the main actors in this process of sending and spreading these messages to high schools all over the world, and how we can design with them, in collaboration with them, innovative scenarios that could explain these quite demanding issues and natural phenomena. So the story starts back in 1930. You can have access to the archive, to Pauli's archive at CERN, and get also the original messages when he is identifying some problems related with the main concepts of reactions, like the conservation of energy, the conservation of momentum. And he is proposing for the first time that there must be a very small neutral particle, and Pauli gave initially the name neutron, and Fermi a few years later call it neutrino, meaning the little neutral one. So this happened 2 years later, and the name was given from Fermi. So Pauli, he's not really ready to publish this work, but he's proposing this to a big conference of researchers at this time, by proposing for first time the existence of this very small particle. It will take about 40 years, and in November 13, 1997, we will have the world's first observation of a neutrino. In fact, it's not an observation, because as Professor Kurkumelis mentioned before, in the search for Higgs, for example, we are not able to see really Higgs, but we see the outcomes of its interaction with matter during the collisions at CERN. In the same way, you can imagine that the invisible neutrino is coming from the right hand of the screen, more or less in the same line with the muon that it is produced, collides with a proton. The proton starts moving, and a muon is produced. So this was about 40 years after the initial proposal of Pauli. Now, how such a, for example, discovery can be used in the school classroom, because the natural concepts, the natural laws are the same, even if we are referring to the microcosmos or to the physics that we are learning at school. So here I'm trying to connect also with the previous presentations. Professor Kourkoumelis presented us how we can transfer the experience at a collision at CERN in order to identify new particles. So the way they are doing that is by calculating their energy, their momentum, and they are trying to identify which are the new outcomes of these reactions. A category of, and I believe that during their workshop in the next days, they are going to explain that when a neutrino is there, is causing problems to them, because it's not helping them to come up with the total momentum, because the total momentum has to be zero in such a collision, because the initial momentum at the cross-sectional plane of the detector is zero, so it has to be the same after the collision. So when this is not happening, and this is such a case, and we have difference, this can be allocating the missing momentum. We can say that this is due to the existence of a neutrino in the specific collision. So neutrinos are there to create problems, maybe to the identification of new particles at CERN, and this is something that we are going to discuss a lot during this seminar, because we are going always to see to have really a balance, try to have a balance between the noise and the signal, and where in one experiment a neutrino could be the noise, for example. There are other experiments where neutrinos are really the signal that we are looking for. So after this small connection to related issues with the school curriculum, some further information about neutrino. The neutrinos are coming from the beta decay, is the outcome of beta decay, and the major source of neutrinos is the sun. This is, if we wanted to describe the sun as a chemistry lab where all these reactions are taking place, this would be the picture of the sun. And the biggest amount of the flux of the neutrinos that really coming to Earth is coming from the nuclear reactions at the center of the sun. This created, apart from let's say the problems that Pauli had in 1930s, about 40 years later, 40 years later, there was another major problem, and the reason was the strange behavior of the neutrinos. If we, let's say, believe that we have a good understanding of how our star is working, and we are able to describe in such a detail the nuclear reactions in the center of the sun, then we will be able, that was the idea, to measure exactly the flux of the neutrinos that are coming to Earth. But This was a major problem at that time because the flux that we were counting in the detectors that we have installed inside cavities under big mountains, in old mines, in different locations in the world, gave always the same flux. And this was much less than the expected flux of the neutrinos that we were expecting from the sun. So there was a conflict, really. Is our let's say are our experiments problematic? They are not able to measure the correct flux, or sun is not working as it was expected. And there was this guy. It was the youngest member of um, the team of Fermi in Italy. And his name was Bruno Pontecorvo, that proposed that there is nothing wrong with our experiments and the experimental devices and techniques, and there is nothing wrong with the sun. Everything is working as it has to be, but it's the neutrino that is causing this problem. And it was the nature of neutrino that is really acting and playing three different roles and is changing from one state to the other while it is moving inside the mass. And this phenomenon is called neutrino oscillation. Don't forget that the Nobel in 2015, in my second slide, was awarded because of the discovery of neutrino oscillations. So the first formula here describes that an electron neutrino is coming, let's say, from specific states that the neutrino can be. And during the time, while the neutrino is traveling in the matter, it can change from one state to the other. And so we were expecting electron neutrinos in our detectors, but they can be transformed to muon neutrinos. So when they have calculated all the fluxes from the different kinds of neutrinos, then the flux was correct. And in this case, we were sure that we have understood how really the sun is operating, the center of the sun is operating, and at the same time, we have identified a really strange phenomenon, the neutrino oscillations, that are connected with the mass of the different states of the neutrino. So the second one that is giving us the probability of changing from one kind of neutrino to another, it is related to the difference of the mass of the different kinds of neutrino and the distance that the neutrinos are traveling inside the matter. In 2002, the Nobel Prize is given for the this first neutrino image of the sun, and we have to say that let's say about 100,000 billion of neutrinos pass through your body every second, coming from these interactions. And statistically speaking, during our lifetime, only one is going to stop inside our body. So this is how rare the interactions of neutrinos with matter are. And we have to say that from one side, there are numerous neutrinos out there, but they are reacting with the matter very rarely. So this makes their also detection a major issue. So these are two images of the detectors that measure really the neutrino oscillation, Super Kamiokande on the left and Sunbury Observatory on the right, following a bit different techniques in order to measure all the fluxes from the neutrinos. And moving now to the birth of neutrino astronomy. So now we are coming in 1987. A large supernova explosion is taking place at the Large Magellan Cloud at a distance of about 168,000 light years away from Earth. And the neutrino detectors in the old mines all over the world are suddenly detecting a huge number of neutrinos. Specifically, Kamiokande detected 12 of them, IMB 8, Baksan 5, and so on. And in a very short time frame. That means that the flux of neutrinos that cross the Earth in the specific in this short time window, it was amazing. So immediately they are starting a series of calculations in order to find and relate this flux with the specific phenomenon, the explosion of supernova 1987A. And this is considered as the starting point of a new really era in the field of astronomy, because it's the first time that we are able to locate a source of neutrinos by using these small scale detectors that they were located in the mines. So this is the picture of supernova 1987A. The star that exploded is presented on the right figure, and the explosion is on the left figure. And some years after, the dust is still moving away from the center of the explosion in the Large Magellan Cloud. So this was the starting point of developing much bigger detectors, because the small ones in the old mines, in cavities inside the Earth, were not enough really to detect such kind of events. So we had to build much bigger detectors, either to the Antarctic ice or to initially in Lake Baikal, later in a Pacific Ocean, and also in the Mediterranean Sea. The process is similar to the second slide that I have shown you, let's say the reaction of a neutrino. A very high energy neutrino coming from space is reacting with the matter, is producing a high energy muon. It's almost in the same line. This is very important, because in astronomy, in order to do astronomy, we have to know the trajectory of the initial particle. So this high energy muon is now entering to the sea and producing Cherenkov light, because the muon is moving faster than the light inside the seawater. So when a particle is moving faster than the light in a specific medium, is producing Cherenkov radiation. And this is a blue cone at a specific angle, that is helping us to really reconstruct with high accuracy the trajectory of the muon. And if we manage to reconstruct the trajectory of the muon, then we have a very good estimation of from where this high energy neutrino is coming from. So you can understand that a neutrino telescope is a detector in principle of blue light. We have to put them very deep in the sea in order not to be affected from any other light source at a depth of 4,000 meters, to have enough space in order to create a very big detector, in order to be able to see these very rare interactions, and they are looking downwards. So they are looking for neutrinos that they are coming from the other side of the planet. So we are using the Earth as the main target for these neutrinos. We are giving them a lot of mass to interact, and we are hoping to see these signals. How we see these signals? We have the so-called optical modules, photomultipliers that are able to measure even one photoelectron in principle. So this is some pictures from my background many years ago, about 30 years ago, when we made the first attempts in the Mediterranean Sea to deploy parts of this detector to prove the overall concept on how such a telescope can work. The first efforts took place at the southwest end of Peloponnese, where the African plate is entering under the European plate, and at a very deep sea area that goes up to 5,000 meters under the surface. And these are some structures of the initial part and the initial design of the detector, having the form of a whole tower with numerous floors. It was about 300 meters high and 30 meters in diameter, this whole construction. And many, of course, other research efforts took place at the same time in Italy, in France. One was Antares, that has deployed the photomultipliers in another structure using a string structure, not the floor structure as it was presented before. And now these efforts are coming all together, developing a kilometer cube neutrino detector at near in the Mediterranean Sea at the south part of Sicily, which is going to be, let's say, the major research infrastructure for neutrino astronomy in the next years. So some examples here of how these muons are coming and activate the different detectors. So here you see a muon coming downwards. So this is, let's say, a muon that has been created in the atmosphere and is approaching the detector. There are numerous such muons that are, in the specific case, noise for the telescope, because these are not the muons that we are looking for. We are looking for such muons that are coming from the bottom and they activate the detector as they are moving upwards. So these are the muons that we would like to see, the muons that are coming from the bottom of the sea. The presentation is going to be available, and you can see these animations anytime you wish. And now from fishing for neutrinos in the Mediterranean, I'm moving to ice fishing for neutrinos. Installing such detectors in the ice proved to be an easier process because the experiment, the large infrastructure that is being installed last years, for many years, but now it's really expanding significantly in South Pole, in the Antarctic ice, has moved much faster than the efforts that were made in the Pacific Ocean and in the Mediterranean. So there, the ice, the Antarctic ice is too thick. It's going up to 3,000 meters. So the researchers there are opening holes with hot water. They are going down to 2,500 meters to 2,000 meters, and they are installing the photomultipliers there. And here in the picture, you can see that again, the structure is quite big. It's a very big structure. This is the size of the Eiffel Tower, just for comparison. So this is an image of an optical module, the eyes of the telescope that are being lower in the Antarctic ice. Then everything will freeze. They have about something like 2.5 hours to lower the detectors inside the ice, and then they will be freezed forever, and they will start collecting data. This is the whole center, the South Pole. In 2013, they are making the first announcement measuring very high energy events in their detector. It's going up to 100 times the energy that we are giving to particles at CERN. So clearly, these events are coming from very high energetic structures in the universe, and the aim is, having proved the concept that we are able to measure them and that they are there, to identify where they are coming from. And this is the major task. Some other images of very high energetic events: the bigger the cycle and more red, more energy is reading on the detectors in the strings. The very small white dots that you see are the photomultipliers, while the green, the yellow, the red are the activated photomultipliers from the different events. I think among the most energetic ones is this event that was detected in 2014, approaching 4.5 thousand TeV, 1,000 times the energy that we of the protons are getting at LHC. So where these events are coming from. So these events are coming from the centers of the active centers of galaxies, where we believe that there are supermassive black holes that are creating, let's say, the conditions for particles to achieve this energy, to get this energy. And there are models for describing this process. So you can see here, I will go one slide back, and you can see that from the center of the galaxy, where this structure is, and we believe that there is a supermassive black hole, jets of particles are emitted. So when we have the, let's say, the chance, these jets, to target Earth, we have really the opportunity to detect the outcomes of these interactions, which are the muon neutrinos that I mentioned before. So this is what we are looking for. We would like to create a map of the universe by locating such let's say, cosmic accelerators that are really powerful accelerators of particles, and construct this map of the universe. In 2017, in September, quite high energy, about 300 tera electron volt, is arriving to the detector in the South Pole, and immediately an automated alert is sent to other detectors and telescopes across the globe in order to identify the source of this muon neutrino, and of course the neutrino that it came from this. And it's the first time that we have really managed to identify a point source, a blazar, very close to the area where the reconstructed track of this neutrino yield us, and this is the specific blazar that gave this very strong signal. With this one, I conclude my presentation. I would like to mention that for many years, working with also the previous speakers, we are trying to connect Nobel Prize physics with the high school curriculum. And the aim of our seminar is really to try these quite, let's say, complex concepts to present them in such a way that can be transferred to a school classroom by analyzing all the different components of the detection process, the techniques, the phenomena behind it, in order to demonstrate that the natural laws are the same as the ones that are presented in the school books. So thank you very much for your attention.